So radical chemistry. This intent here is to cover the bare minimum basics of what's happening behind radical reactions, and that is about it. First and foremost, why radical reactions? Most of our chemical world as we know it comes from petroleum, and petroleum-based substances are largely alkane-based. The problem with alkanes is they're virtually non-reactive. All London dispersion, these are non-polar covalent bonds. These just aren't reactive. So to get them to react, we have to do something, forgive the pun, radical to get them to initiate. That's where our radical reagents come in. So ultimately, the whole point of radical reactions is to make an unreactive molecule reactive. Where radicals start comes from kind of an interesting basis. Radicals are Merry Christmas, it's late. A product of a reactive bond, okay, splitting in a non-standard fashion. So for instance, if we take a look at this molecule, what we're looking at here is actually O2. And if we look at the molecule of O2, we might say it's nice and stable, and it matches all the standard patterns that we've seen before. It turns out that O2 has some interesting chemistry with it, and that chemistry is radical-based. If we take a look at the pi bond, it can actually split where each oxygen takes a single electron away from the pi bond. This results in what is known as a diradical species. Diradical because we have two oxygen atoms with a single unpaired electron. Electrons want to be paired, hence the reactivity of our radical species. So if you've heard about free radicals free radicals are bad and we need things to protect ourselves from radicals. Radicals are important because that's how we live, is actually based off of radical chemistry, but it's uncontrolled radical chemistry that becomes an issue. So our biological systems have created ways to scavenge radicals, and in the operative word being scavenge free radicals. So they're ultimately generated by having these kind of exceptionally weak bonds. If we look at the structures I've got drawn here, these are kind of standard radicals, and if we expanded those out to look at their parent structures and where they could have come from, and this last one is not an easy one to look at, so don't stress about that. Each of these compounds are where our radicals are initiated from, and they each have two very electronegative elements sharing electrons. Those electrons aren't particularly nicely shared, and because they have an equal force on the electrons, they can split, given the proper circumstances, homolytically as opposed to heterolytic. So the heterolytic bond cleavage that we're used to seeing, so our hetero, is paired electrons. This is where we have curved arrows that have a double head. Radicals are all about homolytic bond cleavage, and that's now single-headed arrows. The electrons in the bond, I now have to define where each and every single one of them goes, and it's going to a different location. So we're going to need more arrows to discuss radical chemistry. Okay? The next part, their mechanisms aren't as simple and straightforward and not very linear. You get all sorts of weird, crazy stuff happening. So when we think about radical reactions, we break them down into kind of basic mechanistic steps. The first of those steps is an initiation. Okay, so I need to make the radical. So that's starting typically with Br2 is a good starter offer, for lack of a better word. The other one is that peroxy bond. Okay, sometimes it's shown as a symmetric peroxy acid. I don't know why I decided to just redraw it again. Sometimes you'll see it actually written out as just R groups. So you'll hear people reference ROR. ROR means radicals. The other thing that you could see would even be peroxide. Peroxide can also initiate radical reactions. In both these cases that we're looking at, either the ROR case above or the bromine case below, we need to get that bond that connects those two electronegative elements to break homolytically. There's two ways to go through and do this. One is just with heat. Okay, this tends to work better with your raw molecules, and what will end up happening is we vibrate the bond enough that the electrons scatter to the opposite oxygens. The end result is that we get two radical structures. Or we can use H-nu. H-nu, which you should remember all the way back from 151, is just a way of representing the energy for light. Light can be used to excite a single electron in the HOMO up to the LUMO. You've now broken the bond. Okay, it's literally broken the bond by using light of the proper wavelength. Same result, we end with the radical. So lesson, initiation, no radical, ends in radical. That's an initiation step. Okay? So, next step, what can those radicals then go out and do? This is now looking at your propagation. Okay? The propagation tends to be very heavily concentration dependent, and that's where radical reactions become tricky, is because we don't bring concentration into our reactions. So it becomes an implied aspect of those reactions. When we look at the actual reagents, I'll be pointing out and saying, hey, this is one that we have a lot of concentration on. So if we go through and look at some example propagations, we're starting with a radical. The most likely thing for that bromine radical to encounter in that next molecule is going to be a hydrogen. Remember, radicals are not stable, so it's going to try and pull off the most accessible thing. So it would be a hydrogen. So we could have it pull a single electron from above. Okay, remember the bond has two electrons in it. I'm going to have to show where the other electron goes. Okay, that result would be here. Okay. Or I could have had that radical go with the other hydrogen, and that would have formed here. Okay, so I get two results. How do I decide which one is the primary product? Well, a lot of that has to do with the reactivity of our radicals. Bromine is the most useful halogen radical initiator. Okay, and the reason for it is that it is what is known as a selective reagent. If we go through and look at our bromine radical, it is relatively stable, whereas the carbon radicals, not so much. So we're looking at a very endothermic reaction. What this means for us is that when the bromine radical reacts, it will react to form a carboradical, there's got to be a better word than carboradical, a carboradical that is more stable. Okay? Which means when I look at those two reactions, the most likely product to form is actually going to be this guy. Okay? Chlorine, on the other hand, if we were to look at the same energy diagram, because chlorine's also a halogen, I could throw chlorine into this diagram. Chlorine as a radical is much higher in energy than bromine, and that's because it's smaller. Okay? So what happens now is we're still forming the same carboradical, but now it's an exothermic reaction. Well, because chlorine is so much more reactive, it's reacting with whatever it can encounter first. Okay? So it's going to react with everything, which means we would get both products if I ran with a chlorine radical. If I move up to a fluorine radical, fluorine radicals are so insanely reactive that they're never used in radical initiations, because what happens? The reaction container explodes. Okay? That's not a useful reaction. That's how fast those are. Iodine, on the other hand, is now so stable that it becomes a very selective reagent as well, but it becomes so selective that the reaction never happens. It's just that incredibly slow. That's really why bromine is the only useful radical reaction. Okay? So again, if we go through and look at the basics, we started with a radical, and then we ended with a radical. That's a propagation. A radical reacts to make a radical. It doesn't have to be the bromine radical, because if we take a look, we formed carbon radicals. Well, those carbon radicals could then react with the next most likely thing, which could be bromine in this case. Okay? What's the end result? We've now formed a new product, a new carbo structure that actually has a halogen attached to it. We now have a reactive species. Okay? Reactive according to our heterolytic bond cleavage, or really our standard chemistry that we've been talking about. Okay? So that's pretty cool. Okay? Now all we would have to do is to stop the radical reactions, because if there's still radicals present, all sorts of crazy stuff can still continue on. This is why we would then kill the reaction by throwing in radical scavengers that would react and pull the radicals out of solution. But ultimately what happened is I started with an alkane with virtually no reactivity, and I can convert that into an alkyl halide that actually has a sizable amount of reactivity. Okay, and that's kind of the point. Take something with nothing to make it something. So that's our primary driver for our radical reactions. Take alkanes to alkyl halides. Okay, there are other cases, but that's the primary one. Okay, notice in this case, when we talked about this, we said we wanted to form the most stable radical, which brings back some content that we talked about earlier on when we talked about the stability of, say, carbocations and carboanions. The cations we wanted tertiary, the anions we wanted primary. Well, where should the radical fall in that scale? Is it more like a cation or more like an anion? And it turns out that it matches much better to the cation chemistry. So if you can remember radicals equal cations, when you run a reaction that you suspect is a radical, make the radical chemistry happen at the most substituted position, or the most stable place where you would think to put a cation. And I'm using massive air quotes, which I know you can't see, but I'm doing it anyway. Okay, so it's roughly a cation. I want it to be the most stable thing here. Before somebody calls me out on it, I know that's not a tertiary, but it's tertiary. It's the most tertiary in this case. Okay, it's a secondary. So, products being favored, we want to form the most stable intermediate. We're going to end up with the secondary one in this case. Okay. The last thing is now the end of the radical. This is going to be the termination. So if we look at our termination steps, we're starting with radicals, but we're starting with two radicals. When those two radicals come together, what happens? No more radical. Okay. So it's the death of our radical. There are tons of different ways that termination reactions can happen. And in fact, if we go through and take a look at these, those are actually probably the least likely ways to terminate. Okay? Because all of those are based on concentration of the reagent radicals in the solution, which are really, really, really tiny because radicals aren't particularly stable. Okay? But it is because of these kind of reactions that we can get goofy things happening like this guy in the bottom of that. Okay? So we can get two radicals reacting with each other. All of that is concentration dependent. So you would have to very carefully select how much of your reagents you want present in that radical reaction. Again, none of that shows up in our overall reactions. Okay? So this is where radicals would become a more important subject that you would then want to discuss if you were, say, moving into the field of petroleum-based products. What's the more likely scenario? The more likely scenario is that I've decided that my reaction is run for long enough that I've maximized the yield of my targeted compound. In this case, that upper right-hand corner alkyl halide. I've got roughly the same amount, or the largest amount that I want. Radicals are now potentially decomposing this. Okay, that says decompose, and that's bad. Okay. How do I know that? It comes with experience within time in the reaction and just seeing that the yield of that product starts decreasing. So once I've achieved that rough time, what I will do is throw in a scavenger. Okay? That radical scavenger will seek out our bromine radicals, or any radical for that matter, and neutralize it. Okay? Which then stops the reaction. I can then work it up and get my ideal alkyl halide out of the solution. Okay? So again, as a quick summary of all of that, if we go all the way back here a little bit, we've got initiation, formation of a radical, propagation, radical reacts to make a radical, and, termination, the full loss of a radical. Okay? Why? Okay, well, alkanes don't have any reactivity. If I again pull out my petroleum product, let's just say petrol, there we go. how could I possibly get it into, say, a structure like this, okay, like what we found in lab? Well, the first thing I might want to do is run a radical reaction. That radical reaction will be able to convert this structure into an alkyl halide. That alkyl halide could then potentially react in an elimination type fashion to get me that product. How do I know I need to do that? Well, there's a couple ways to do that, or know to do that. Number one, I can look at the starting material. My starting material is an alkane. The only thing I can use to react with alkanes is radicals, so I know I have to be doing a radical reaction. Or I can think in the reverse. Okay? That's a pi bond. That's the site of reactivity of this structure. Well, I know I would form pi bonds if I'd done an elimination reaction. How do I do elimination reactions? Well, I need a leaving group. So somewhere there needs to be a leaving group on the structure. Because I want to form the most stable pi bond possible, it's going to make sense to put my leaving group there. Okay? What's a good leaving group? Well, a good leaving group would be something like a halogen. Why the halogens? Well, they have no other reactivity. They can only act as leaving groups. If I'd picked, say, an alcohol, the problem with the alcohol is that the alcohol functional group has other chemistry. Not only can it act as a leaving group, but it also has an acidic hydrogen. Okay? It also has a basic oxygen. So the alcohol functional group becomes way too tricky to deal with. It makes sense to do the elimination from the halogen. Once I know I have that as a structure, I then need to do some kind of radical reaction to get me that. Okay? Notice, conveniently, I've placed the leaving group at that location. Why did I place the leaving group there? Well, I did it based off of the elimination chemistry. That's why it was placed there. I also conveniently noted that that works for the radical. If I'm look at an alkane and I say, I have to do a radical reaction, okay, that radical reaction right now is to put on a halogen. Okay, to do the halogen, it needs to go to the most substituted position. Why the most substituted? Because the most substituted position is the most stable radical. Okay, you don't like radicals? Then what should you remember radicals to be? Cations. Where's the most stable cation? If I was forced to draw a cation into this structure, where would it go? It's going to be the tertiary position. That's where I want to do my reaction. Okay, so that's why it's helpful to tie radicals and cations together. Okay, so that's kind of the point of our radical reactions. Okay, so I can convert alkanes into alkyl halides, and then I can do all the normal reactions I've already done. There's really only one reagent, okay, and we did kind of talk about this already. Okay, bromine is the big one. Okay, it's the selective one. Sometimes you'll see chlorine. It is not selective. Okay, meaning if I ran the chlorine reaction with this structure, I get tons of products. I could put the chlorine there, 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 I could put the chlorine there. That's why I can't count 1, 2, 3, 4, 5 different products. If I run the bromination reaction, I only put the bromine here, and that's it. Okay, so that's what we're talking about with selectivity. Chlorine is non-selective, meaning it goes wherever the hell it feels like, so wherever there's hydrogen. Bromine, being selective, is going to go specifically to where there's hydrogen. Okay, if we go through and look at other halogen as reagents, the fluorine is too reactive. Okay, so that explodes, so we don't want to do that. Iodine is insanely selective, but it is so selective that it never reacts. Okay, so bromine versus chlorine, here's that energy diagram that I already drew out, showing or helping you to see that difference. If we look at the bromine reaction, okay, our transition state is closest in energy to our products. In this case, the more stable the radical, the lower the activation barrier. That's the one I see. When we move to chlorine, the chlorine radical is so much more reactive than the bromine radical that the reaction switches from being endothermic and thus selective to becoming exothermic and not selective. Okay? And so now, well, what's going to dictate which product I get? Well, I'm going to get the product that I can form the fastest, because the energy diagram has virtually no difference in energy on the transition state. It's just going to come down to which one I can make faster. Okay? That making faster has lots of different options. Okay? There's more hydrogens to do reactions at the end than there are on the inside. So concentration becomes an issue. This is why we tend to not use chlorine. Okay? So, if given a choice for a synthesis, choose bromination. If you're forced to, you can do chlorination, okay, with chlorine, but realize it's just going to react as fast as humanly possible. You're going to get a crap ton of products. Okay? Stereochemistry, you're forming a radical. Radicals are carbocations. Problems with carbocations, they can react from above and below, which means when we think about optical reactivity or optical activity, we're going to get two products, okay, or two potential products. We have to decide you F nugget. God, now I don't even know what I'm writing. Two potential products, okay? How do we decide the relationship between those two products? We'll draw one and see what happens. I'd be putting the bromine on there. What do I mean by see what happens? Is that a chiral atom? If that's chiral, you got two products. They're at least enantiomers. Okay? Is it the only chiral atom in your structure? Then they're enantiomers. If there's another chiral atom, say over here, then you've got diastereomers. Okay? So you do have to watch out for this potential two-product enantiomer just mess with you. Okay? So pay attention to that. Okay, the next part, when we talk about cations, we might say, well, in this structure, this would be a great carbocation, and not because it's secondary, but because of resonance. Okay, so is that going to come into play with radicals? Yes. Okay, if I run this reaction, I could end up with very easily doing a bromination reaction there. The problem with this is that if you remember from our electrophilic additions, Br2 is also a good electrophile. Okay, why does that become a problem? Well, what do pi bonds act as? Well, nucleophiles. These same reaction conditions could result in the addition of bromine to the pi bond. Okay, that becomes an issue. The best way that I can limit this second reaction here is to limit the amount of Br2. Less Br2, the more likely I can force the radical reaction. Okay? Is it not inherently obvious? Well, the other big hint, that's light. Light is a giant freaking red flag that you need to be doing the radical reaction and not the electrophile reaction. Okay? So look for that light as your tip-off. Okay? The next thing that we could potentially do is control the amount of bromine present. That can be done through this reagent known as N-bromosuccinimide, okay, which looks like I spelled it wrong. That is often abbreviated as NBS. Okay, the big deal is you have a very weak two very electronegative element bond. Okay, that reagent will react with solution to form very small amounts of bromine. Those small amounts of bromine can facilitate a radical reaction instead of a electrophile addition. Okay, so NBS is usually a good tip-off that you're doing a radical reaction, not electrophilic addition. Okay, so radical substitution reagents. Br2 in light, bromine at your most substituted position. Okay, the weird thing that I haven't explicitly stated, we're actually doing a substitution for hydrogen, okay, which is kind of bizarre. Hydrogen's not a good leaving group because it isn't really leaving, it's reacting off through this nasty radical stuff. Okay, then we get chlorine, which would also do hydrogen, but at all positions. That's the big problem there. NBS and light is really a big tie for your allylic and benzylic positions. Okay, so those are your three reagents where I would argue really you're only going to see 1 and 2. Okay. Next part, Of course, you can do addition reactions because I've only got 6 minutes till I hit half an hour in recording and the battery dies. So in a radical addition reaction, we can switch it up and use, instead of bromine, we can use our ROR. Okay? What happens with the ROR is it then splits out into our radical. Well, now what do we add? If we take a look for our addition reaction, we're going to start with our standard strong acid and our standard alkene. If that's all we added, we might expect the product where we would put the bromine there and our hydrogen at the place that already had the most hydrogens. Okay? But we're also adding this radical. Okay, so here's my cheat. Do you recognize that ROR is there? Radicals are happening. What do radicals do? They F with everything. Okay? Because I know it F's with everything, probably not going to be doing the standard addition, which means the non-standard addition, I'm going to put the bromine there and the hydrogen there. Okay? Radicals F with things. Remember that. Do the opposite of what you think they should do. And guess what? The blue is the answer here. Okay? Why is the blue the answer? Okay? Well, the first thing that radical encounters is going to be the HBr, okay, which means we form bromine radical. What is that bromine radical now going to react with? Well, it's going to react with our alkene. Okay? When it reacts with the alkene, we could then produce two potential products. Okay? One, where we have the bromine connected here, and then remember, what else? That's a pi bond. There's a leftover radical electron. Or we could have run the reaction where the bromine goes out here and the radical goes in here. Well, which of those two radicals is more stable? Oh, that's right. Radicals are roughly cations. This is a secondary versus the top one being a primary. The secondary is more stable. What's the most likely structure for this new radical to encounter? More HBr in solution. And we would end with our final product with the bromine connected. Totally easy, right? That is sarcasm for the record. Okay? And that's how we end up doing our radical additions. Okay? So we need to be aware of that. This also then means we've got a couple things that we've got to do around our alkenes. There's two ways to react them. We can do it with NBS, and if we react with NBS, what happens? And of course I picked a structure with 5 million possible freaking products. With NBS, we can do our radical substitution, okay, where we're putting the bromine at the allylic position. Or I can use my ROR and my strong acid, and that's going to add hydrogen and bromine across the pi bond. It's going to add them, though, the opposite way that I would expect. Okay, just for the record, opposite way I expect. If we drew out a resonance structure, positive, negative, a resonance structure for HBr, horrible resonance structure, but whatever, positive and negative, I would expect my positive to go to the negative. I would expect the negative to go to my positive. Notice, not what happened. Okay, why not? Because it didn't split heterolytically. It split homolytically. Everything goes sideways. Okay, we can't use those positives, negatives anymore to help us predict. We have to use something else to help us along that line. Okay, you could see something like the Birch reduction. You can do this with alkynes. We will kind of talk about this one in class. Okay, ultimately, what you need to do is just kind of memorize that if you have a triple bond and you react it with sodium metal, shown as Na solid in the presence of ammonia, that you can reduce that down to an alkene. What becomes interesting about this one is you get the trans product here, which is non-standard for our reductions of alkenes and alkynes. We typically get the cis. Why do we get the trans? Okay, well, what do we end up forming? Mother effing radicals. That's why we're getting weird results. Okay, it's all because of those radicals messing with those systems. And it's not really that they're messing with it, we just aren't used to working with them. Okay, because some jackhole talked too much about other stuff the whole semester, and you get to watch this in a video. Oh well. Okay, the Birch reduction can also happen with benzene structures. Don't worry about this one at all. This is second semester. We will talk about it probably in an equally fast, stupidly short video at the end of the semester. Okay? So don't stress on this one, but it is kind of neat. If you wanted to, you could think about it, how those reactions worked and why they would work. Okay, so addition reactions with radicals. If we focus on our reagents, we could go through and end up with our nice little results. Yippee-ki-yay, isn't that fun and dandy? What happens if we move to that bottom case? Okay, this becomes an interesting one, because if we go through and did this reaction, we would get our ROR forming our radical. Well, now what does this radical have left to react with? The only thing it has left to react with is more starting material. So it reacts again, forming another radical. So it reacts again, forming another radical. And what we end up forming, okay, is a polymer. Okay, this is known as a radical polymer. Polymers do have the potential for showing up on your exam primarily in the form of radical polymerizations. Depending on how that radical was initiated, you could form different types of polymers. I don't want you stressing a whole lot about it. Just recognize that alkenes can react with radicals just like bromine did, just like HBr did. Okay, so there's our big summary for radicals. Okay, everything all fine and dandy, happy on one slide, admittedly missing the nasty little polymerization reaction that could also happen out of there. Okay, so almost in 30 minutes, and I'm pretty much just going to say I'm done with that. So I hope that works. You've got a little bit more background on the radicals. Again, I'll double back. This is the slide that you should memorize.